Okay, so we're going to start today with the multiple choice questions on AP Classroom. Let's just see how those are. That's always the best place to start. And we can round those out with more textbook problems. So let me just see if I can get there. This window like died on me or something. There we go. Okay. Let me bump up the font. I feel like the font's still pretty small. Let's just do that. Huge font. Okay. This thing is so slow. Okay. I don't know why this font isn't bigger. Can you guys read this?
Yeah, I can read that.
I can as well.
Okay. Let's just make it large then at least. I don't know why it doesn't want to. There we go. That should do. That way it'll be a little more readable. Yeah, I like that better. Okay. All right, so we've got this problem. So hydrochloric acid and ammonia neutralize to form ammonium and not really. Man, that's weird. No, it's just a, is that, huh? Is that a neutralization? It should be an acid-base neutralization. Yeah, they form ammonium and chloride. Okay. It's just weird because usually you get a salt and water, but not in this case, and that's okay. Okay, so represented above, a student combines equimolar amounts of HCl and NH3. Both solutions initially at 24C in a coffee cup calorimeter. As soon as mixing reaches a temperature of 28 degrees C, based on the experimental results, which of the following can be concluded? Okay, so give yourself a couple minutes to just think about this. Okay, let's go like 90 seconds. Hey Siri, set timer for 90 seconds.
Your timer is set for 1 minute and 30.
Yeah, this is pretty clear. Yeah, that's right. You can chat privately with me and let me know what your answer is. Yep. Yep, that's right. Okay, about 30 more seconds. Okay, so what's the deal here? So Marcella, what'd you get?
I'm not sure.
Okay. Antonio, how about you?
I got C.
You got C. Okay. And what about you, Symphony?
I got D.
D is in dog? Okay.
No.
So remember, when a reaction is exothermic, it loses heat, right? So the reaction mixture is increasing in temperature because the reaction is releasing heat. So that's C, okay? So this one is for sure C. Idali, what did you get?
I had been thinking between C or D, but yeah, C.
Okay. Yep. That's for sure C. Okay, and we'll go back over all of this and we'll review it. But you're definitely going to see a question like this on the AP test, like no doubt. You might see a couple of them about like this, just because the test is going to test less material, I think, this year. So, okay, but I'm still trying to figure that. I'll give you guys an update tomorrow. I think I got a presentation from Dr. Zhu on that. Okay. Okay, number 2. So when pellets of sodium hydroxide are added to a flask of water, it is observed that the temperature of the water increases as the pellets dissolve. Yeah, I've done this. Which of the following claims about the observed dissolution of sodium hydroxide in water is most accurate? Okay, take a minute, guys. Hey Siri, set timer for 1 minute.
Okay, your timer is set for 1 minute.
All right, so Marcella, what'd you get for this one?
I got A.
You got A, endothermic, because heat energy is absorbed by the water as the NaOH dissolves in. Okay, so the part about the water absorbing energy is absolutely correct. But what's happening to the temperature here?
Increasing.
Increasing, right? So what does that mean, Idali?
That it's exothermic.
Right, it's exothermic, okay? Because this process is releasing heat. So if things are getting hotter while a process happens, that means that the process itself is releasing heat, okay? So this is an exothermic process. All right, so I want to hear from Symphony. Symphony, what's the answer?
I think the answer is D.
D, by the water. Is the water releasing heat energy?
No.
No, not the water. The water is not releasing the heat energy. The sodium hydroxide dissolution is releasing the heat energy. So essentially, when this sodium hydroxide, that's not a good way to think of it. When this guy gets solvated, it just releases heat. And so that makes the correct answer C, okay? Because this thing's dissolution is releasing heat into the water. Okay. And let's see, do I get to double check on this one? Double check. There we go. Okay. All right, so number 3. Okay, so an advertisement for a commercial. Sorry, any questions about number 2 before we move on?
I'm good.
Okay. All right. So number 3, an advertisement for a commercial hand warmer claims that the hand warmer works because a chemical reaction in the hand warmer draws out the body's own natural heat, causing a warming effect. Which of the following states the accuracy of the claim in the advertisement and best provides a correct scientific justification of the claim? Ooh, okay. So this one's going to take some thought, okay? I want you to think about it for about 90 seconds. So hey Siri, set timer for 90 seconds.
Okay, your timer is set for 1 minute and 30 seconds.
Okay. All right. So Antonio, what'd you get for this one?
I got A.
You got A. Okay. Jacob, how about you?
I was thinking D.
Okay. What about you, Idali?
I got A.
A. Marcella?
I was between A and B.
Okay. Symphony?
Between A and B.
Okay. Kaiten?
A.
Jacob? Jacob, you already answered, didn't you?
Yeah.
Okay. Yeah. So let's take a look, right? Claims the hand warmer works because the chemical reaction draws out the body's heat, right? So if you're holding something and heat is leaving your body and going into that thing, how is your hand going to feel?
Cold.
Colder.
Cold, right? And so if a chemical reaction is drawing heat out of your hand, what must it be? If the chemical reaction itself is absorbing heat, what is it? Endothermic or exothermic?
Endothermic.
Endothermic, right? So the correct answer, everyone, on the count of 3 is 1, 2, 3.
A.
A.
A. Good. Okay, that's correct. Yeah, these guys are some shysters. Okay. All right. So a student carefully drops a 9.0 gram solid zinc pellet initially at 50 degrees Celsius into an insulated cup containing 30 grams of water at 27.8 degrees Celsius. The student predicts that the temperature of the water will increase after the pellet is added. Okay, sure. Which of the following statements is the best justification for the student's prediction? Okay, so here's what you need to understand. This is a 9-gram solid zinc pellet. So this is just solid zinc. It's not going to react, right? It's just it's a hunk of metal, and it's at 50 degrees Celsius, and you're going to drop it into water, right? And so the water is at a lower temperature, 27.8 degrees Celsius. Okay, so what's going to happen? All right, so give yourself another 90 seconds to think through the answers. Hey Siri, set timer for 90 seconds. Hey Siri, set timer for 90 seconds.
Your timer is set for 1 minute and 30 seconds.
Yeah, that makes sense to me, Antonio. Yep, that's correct. No, Idali. Because remember, it stays as a hunk, right? There's no reaction here. Okay, so that's time. All right, so I want to hear from, I'm just gonna go around the room like in a fair way. So I want to hear from Marcella. Okay, I want
I'm
to
not
hear
really
from,
sure.
you're not sure, that's okay. I want to hear from Antonio. Antonio, what do you think?
I think it's A. I mean C. C.
You think it's C. Okay, the strength of the hydrogen bonds are
I
is
mean
gonna-
B. I mean B.
You think, which one?
Wait, which one? Yeah, I put B. B.
B. Yeah, that's right. B. Yeah. Okay, so let's look at all the answers, right? Let's go through them all. B is correct. So let's start with A though. The metallic bonds between zinc atoms will break. No, because there's just no reason for zinc to dissolve. Zinc's not like an ionic compound or something. It's not going to just dissolve in water. I can't think of any metals that just like dissolve in water, but there are some that react. So like lithium, potassium, and sodium, those group 1 metals, those will absolutely react with water. But they don't dissolve. Well, Okay, they do and they don't. They react, and then they ultimately do become soluble species, but it's not a normal dissolution process. It's a reaction. Um, and then so B, collisions between the water molecules and the surface of the zinc pellet will result in the transfer of energy, increasing the average kinetic energy of the water molecules. Okay, so that's true, right? So like you let me draw this out. So you have some beaker, right? And there's water, right? Water in the beaker, and that was bad water. So draw better water. Water in the beaker, right? And you drop this hunk of zinc into the water, right? Right? And all these little water molecules are going to come in and like bounce off of the zinc. And these guys are at a lower temperature than the zinc block. And so as they collide, they'll pick up energy from the zinc. So ultimately, the temperature of the mixture will equilibrate, right? Everything in that water, the zinc and the water, that mixture will reach a common temperature, okay? That's called thermal equilibration. And so that's going to happen. Okay? So that's B. Any questions about what's going on in solution and why B is the correct answer? I want to make sure that we're all on the same page with this because these conceptual questions are very important on the AP test. You're going to see a lot of them.
It makes sense.
Makes sense? Okay. Caton, does that make sense to you?
Yeah, that works.
Okay. So let's go with C. The strength of the hydrogen bonds between the water molecules will increase. That's not true. The College Board kind of doesn't have any options but to give you like, you know, like weird possibilities like this because I don't even know like I don't know if you've ever tried to design a multiple choice test, but it's brutal. Like you're like, okay, how do I like what do I put in here that might distract somebody or whatever? But this is just false. Like the hydrogen bonds, like the zinc isn't affecting the hydrogen bonds. Like I can't even I have a really hard time thinking of instances in which like one thing dissolving or one thing reacting is gonna affect stuff that's like inert or whatever. In this case, you're just dropping in and unrelated. In this case, you're just dropping in some zinc. Like that's not going to affect the strength of a hydrogen bond. The hydrogen bond strength depends on the electronegativities of the atoms that comprise water. So oxygen and hydrogen. It has nothing to do with whether there's some zinc dissolved in the solution, or sorry, not dissolved, but added to the water, so mixed in. D, collisions between zinc atoms and in the solid will increase in frequency when zinc is exposed to water molecules. No, the zinc atoms actually are gonna collide less with each other or vibrate less because their temperature is going to go down. So also, they're not going to somehow like bounce into each other more because they've been added to water. Okay? Okay. Now, what is interesting is that they would collide with each other a little bit faster as their temperature rose if they were added to hot water. But that's just vibration. I wouldn't really call it collision. And then the other thing is really still what would be going on in that case would be transfer, of heat through the surface of the zinc and water interface. Okay. So any questions? All right, let's take a look at number 5. Okay, so 2 aqueous sodium chloride solutions of equal volume and concentration were kept in flasks and held at different temperatures. Okay. Okay. So the solutions were combined in a larger flask. Based on this information, which of the following predictions is correct? Okay. So take a look, take about 60 seconds. Hey Siri, set timer for 60 seconds. Hey Siri, set timer for 60 seconds.
Your timer is set for 1 minute.
Okay. So I want to hear from, let's go with Idali. Idali, what do you think?
Is it C?
Is it C? The particles in the cooler solution and the particles from the warmer solution will reach thermal equilibrium through collisions, at which time the average kinetic energy of the particles in the mixture will be lower than the average kinetic energy that the particles had in the cooler solution. Okay, so there's something wrong with that. Who can tell me what's wrong with that answer?
Is it that the average kinetic energy will be lower than the cooler solution?
Yeah, so this one's almost correct, but there's this one word that's wrong. Will be higher. Okay, because the temperature is going to average out. It's going to be between the temperatures of the two solutions. So that's wrong. Okay, because of that one little thing. Otherwise, that's a great looking answer. Okay, so yeah, go ahead. Okay, all right, that's correct, Kaiten, and thanks for the heads up. Okay, so I want to hear from. Let's go with Symphony. Symphony, what do you think the right answer is here?
I think the right answer is B.
B as in boy. Yeah, why do you think that?
Well, so the cooler solution and the warmer solution will average out, right? So
Yep.
it can't be A because it doesn't make sense for the average kinetic energy to decrease if the temperature is going up compared to the cooler solution.
Mhm.
So because the solution's getting warmer, the kinetic energy will increase.
Yeah, that's correct. Okay. How many of us had B?
I did.
A few of us. Okay, very good. So B is the correct answer. Very, very good. Okay, any questions? All right. I'll go ahead and erase the board there, and then we'll move on. So let's look at number 6. Okay, the table provides data for, what is this? 2 something with methanol. Based on this information, which of the following statements describes what happens when these samples are initially mixed? So these looks like methanol samples. Okay, and why? All right, so okay, got it. So this is so funny looking. Let me see if like if I decrease the font size, would that fix this situation? No, it still looks horrible. It must be a browser issue. That's weird because Chrome should be like the first browser everybody optimizes for. Okay. All right. So take a look, okay? Take a look. Give yourself 90 seconds, all right? Looks like a similar problem to the last. Hey Siri, set timer for 90 seconds.
Your timer is set for 1 minute and 30 seconds.
Yes, Idali, very good. Good job, Antonio. Very nice.
Thanks.
Jacob, the other guys didn't get that one. Okay, there's something wrong there. So see if you can figure out what's wrong with that one. Okay. So, what do we think? I want to hear from, so a few of us have gotten this right. I want to hear from Marcella. Marcella, what do you think?
I'm not sure.
You're not
Not
sure.
really.
Okay. Have you narrowed it down, or have you identified any as incorrect?
I've narrowed it down to C or D.
Okay. Let's take a look at them both. Let's start with C. Okay, the methanol molecules from sample 1 transfer thermal energy to the methanol molecules in sample 2. And does that make sense that these would transfer to sample 2? And why does it make sense?
Because the initial temperature is higher than.
Good, very good. So they are going to transfer energy, right? Because
Mhm.
sample 1 has a higher density. Now look, these are both methanol, right? So is one
Mhm.
sample going to have like a significantly higher density than the other?
Yes? No.
They're both the same thing. They're the same
They're not.
chemical. So would one have a noticeably higher density than the other?
No?
No, because they're the exact same chemical. So that's why C is wrong, okay? In truth,
Okay.
sample 1 has probably a slightly lower density than sample 2 just because it's a little bit higher, but that's negligible. We don't take that into account. That's not going to affect, thermal transfer. But D, right? Sample 1 transfers thermal energy to sample 2 because through collisions because the average kinetic energy of the molecules in sample 1 is greater. Okay, what's the value there that lets you know that the average kinetic energy of the molecules in sample 1 is greater?
Could you repeat that?
What's the value in the table that tells you that sample 1 has molecules of greater average kinetic energy than sample 2?
Because the initial volume is lower, but the initial temperature is higher.
Okay, it's really just the initial temperature. So the volume tells you that there are fewer molecules in
Okay.
sample 1, but the temperature being higher tells you there's a higher average kinetic energy. Okay?
Mhm.
Yeah. All right. So that's correct. D. How many of us got D, scholars?
I got D.
E.
Yeah, good. All right. Let's take a look at number 7. Okay, 7. The graph above shows the changes in temperature recorded for, what is this? Okay, I'm going to lower the font size or something. No, I'm just going to leave it like it is. For, what is that? 2H2O or something? In, what the heck? A constant volume container in which a 1 gram sample of benzoic acid was combusted. Okay, so there's some water in a container and the water is absorbing heat as the benzoic acid is burned. Assuming that heat was not absorbed by the container or lost to the surroundings, that the density of the water is what you would expect or something. How much heat was released? Oh, golly, this sucks because you can't even tell what you're looking at. Let's see if this helps at all. I really don't even know what this problem is saying. Oh, grief. What the heck? 2.0 liters of H2O. So 2 liters of water, 1 gram sample of benzoic acid is about 4.2 joules per gram degree Celsius. Okay, that's what you need to know. So you've got, oh, that's bad. Okay, so you've got, all right, so you've got 2.0 liters of H2O. You've got, golly, I hope that, is that liters of H2O? Oh, I hope so. It's got to be 2.0 liters of H2O. Oh, sweet mercy. 2.0. Oh, that's the worst. Does anybody else have a better? Oh, come on.
Oh boy.
What? 1,000, 1.00 gram per mil. Is it mil? What are we dealing with? What are we dealing with? I can't read this stupid thing. Okay, it's
Oh.
not liters. It's 2.0 milliliters of H2O. What am I looking at?
No,
What are these
okay.
numbers?
This is number 9. Wait, which number is this?
Number
11?
7.
7. Okay. Yeah, so it's 2 liters
2
of
liters?
water. 2 liters of water.
2 liters
And
of water. Okay.
the density is 1 gram per milliliter.
Yeah, the density is 1 gram per milliliter. Yeah. So I'm gonna do the conversion for you because like forget this.
It's
But
just
like if you got
2,000 grams.
2 liters of water, that means 2,000. Well, I guess you should have to do it yourself. I'll let you do it yourself. You can do the conversion yourself because you kind of have to be able to do that. But it's 2 liters of water, and then that's 1 gram per milliliter.
Mhm.
And then what is this? 4.2 joules per gram degrees Celsius. Okay, that's the heat capacity. So how much heat is released from the combustion of the benzoic acid sample? Okay, and so there's your graph, right? So how much heat was released from the combustion of the benzoic acid sample? Okay, and just overall how much heat was released. So you actually don't care how much benzoic acid was combusted. They just how much heat was released total. Okay, so okay, so let's give this a shot. Okay. So you go from like 22 to 25. That's 3. Kaiten, shoot me a chat for your answer for this one.
Sure.
Okay, very good.
And then number 8 is a mess. I'm not sure what I'm looking at or what they want.
Okay, we'll take a look in a second. All right, so guys, how are we doing on this one? How many of us are making progress versus like how many of us are just like stuck?
I've made some
I'm
progress.
back in my notes.
Okay. Okay. So, Symphony, how are you doing?
I'm fine. I'm just going through my notes.
Okay, that's fine. So let's take about 90 more seconds and then we'll start going through it as a group. Okay, good, Italy. Okay, hey Siri, set timer for 90 seconds.
Your timer is set for 1 minute and 30 seconds.
This really isn't a bad problem at all. You just have to put it all together. It's just like those calorimetry problems we did, but there's just a little more unit conversion to be done. So it's not just like a simple one stepper. It's like 2 or 3 little steps. Not bad. Okay. So, all right. So, Jacob, do you have your answer yet?
No, I've hit a wall.
You hit a wall. Okay, what about you, Antonio?
Same.
Okay, Symphony?
I don't know.
Okay, and then Idali.
I think like B, I think, but I'm not sure.
Okay, so how'd you get B? Walk me through it.
Well, I just tried looking at the graph because I tried doing like
Okay.
the
We
actual
probably,
math.
yeah, we probably want to start with Q equals MC delta T, right? Okay, which is going to equal some mass that you don't have, right? You don't have a mass times 4.2, right? Joules per gram degrees Celsius times what's the temperature change here? Idali, what's the temperature change that you get?
3.
Okay,
Like
so
above.
roughly 3 degrees Celsius, right? That's fine. Okay, that's our delta T. Now the mass is the only like little difficult part. So mass equals, and it's really not difficult, equals volume times density, right? So 2,000 milliliters of H2O times 1 gram per milliliter H2O, okay? The milliliters of H2O cancel out. We wind up with 2,000 grams, okay? So you go, okay? And all of that comes out to right around 24 kilojoules, okay? 24 kilojoules, which is closest to B. Okay, so that's your answer there. Any questions, scholars?
Mm-hmm.
What's your question, Caden?
Oh, no, sorry.
Okay,
Wait, how did you find the temperature change?
the temperature change was from the graph. So it started at right around 2022 and it went up to 25, roughly.
All right.
Yep. Any other questions? Okay, so I'll go ahead and clear the board in 3, 2, 1. Okay, and then let's take a look at the next one. Okay, for an experiment, a 20-gram sample of aluminum. So we'll just write that down. So that's 20 grams of aluminum. Yeah, it says there.
Yeah, it gives you in the
Inside a
table.
cup filled with 40 grams of water. Okay, so no heat is absorbed by the container or surroundings. Which of the following equations provides the correct mathematical relationship for the transfer of heat between water and H2O? Okay, so I see. So, oh, this is fun. Okay, but you don't even have like this. Oh, I see. No, you do have what you need. Okay, it's just this table looks ugly, right? So it doesn't know. What you don't know is the difference in degrees Celsius, right? So this is what you do have. You do have a change in degrees Celsius here, right? Of I don't know what this mess is here. I don't know what this thing on the right is. This is a bit of a question to me. You do have this. So delta T is negative 5.9 degrees Celsius for the aluminum, and it's positive 6 degrees Celsius for the water, right? Initial temperature is 90 degrees Celsius. There are 20 grams, and this is 40 degrees Celsius. There are 40 grams at 25 degrees Celsius. Okay. Mathematical relationship for the transfer of heat between aluminum and water. Okay. So this one really isn't that bad, but you haven't seen it in a little while. Okay. So basically, the heat lost,
Mhm.
Q lost for for aluminum equals Q gain by H2O. Okay, and I'll put absolute value bars around everything for now. Okay, and so we got to figure out the signage. And so one's got the opposite sign of the other. So basically, aluminum's losing heat, and water is gaining heat. So you probably go negative because the aluminum is losing heat. So negative Q aluminum equals positive Q H2O. But then they want some silliness here. So if you've got 0.90 to 4.2, then you're, no, that's nonsense. Like,
Mhm.
that's just plain nonsense. It's just this. Like,
Okay.
there shouldn't be a multiplier. Yeah, it should just be D. D should be the right answer.
Okay.
We
So
haven't done one of these labs this year. It would have been, did we do a calorimetry lab? Did we not, or did we not do one?
I don't think so.
Really?
Oh no, we did.
Yeah.
The washer or the nut in water or something.
Yeah, and then I walked you guys through one of these. That was earlier in the year, but we did this.
Yeah. Okay.
Yeah.
Yeah. So what got me tripped up here is that the table up there is just, it's all spinach. It's pointless because
Yeah, that's true. It is spinach.
okay, because
Uh-huh.
that's the part that tripped me up.
Yep. Yeah. Yep. That's right. Okay. So yeah. D should be the right answer. Let's double check. Yeah. Good. Okay. I'm piping mad if that somehow weren't the answer. Okay. Great. Okay. So any questions about this?
No.
No.
No questions. Okay. This makes sense?
Mhm.
All right.
Yeah.
I'm going to erase the board in 3, 2, 1. Okay. And then let's take a look at number 9 here. Okay. So a student dissolves 8.0 grams of, looks like ammonium acetate or ammonia, I don't know, something in a coffee cup calorimeter. Based on the initial and final temperatures of the mixture in degrees Celsius, what is the delta T of the water reported to the appropriate number of significant figures? Oh, this is fun. Okay.
Mhm.
Appropriate number of significant figures, right?
This is
Ha
something
ha
I haven't
ha.
touched on.
Oh,
Yeah.
that's cool. So how many sig figs do you get? Good luck. May the forces be with you. Hey Siri, set timer for 2 minutes.
Okay, 2 minutes and counting.
I don't think so, Italy. I don't think so. Yeah, everybody's rusty on this. Just give it your best shot, okay? Think through it, and then we'll talk about it as a group in a minute. Yeah, Italy, I think so. I think that's how accurate you are. Uh-huh. Because you get one extra decimal place beyond what's provided, right? By the demarcations. Okay. So Jacob, what'd you get for this one?
I got C.
Yeah, because here's what you get, okay? You're good at 30 and you're good at 20, right? Obviously, so you're good at that digit. You're good at the tens digit. You've also got these marks here for the ones place, so you're good at the ones place, and then you are allowed to by eye estimate one additional decimal place. So you're good down to the tenths place, and so that's C.
Okay.
Okay, that's C. Any questions about
Huh.
that? Double check because we don't spend a lot of time, but yeah, that's right. Okay. Any questions about that?
Yeah. So the convention is it's 1 decimal point past the demarcations on the. Okay.
Yep, that's right.
All right. So the other numbers up here were just again spinach.
Yeah. They were just, yeah, exactly. But I mean, this is legit, right? Because you're looking at a thermometer and you got to figure out what you're dealing with, and that looks like a normal thermometer
Okay.
to me. Okay. All right. So number um number 10, evaporation, condensation. Okay, particulate models of the evaporation of liquid water and the condensation of water vapor are shown above. Based on these models, which of the following accurately compares the energy changes associated with each of the phase changes? Okay, so this is interesting, right? So give this a good read, okay? Take a solid 90 seconds. Hey Siri, set timer for 90 seconds.
Your timer is set for 1 minute and 30 seconds.
Yeah, Antonio, that's what I got too.
So just as a quick aside, I was scooting a couple of problems ahead, and I saw one involving a thermite reaction.
Ooh, thermite.
Yeah, and I was so amazed by like how simple it was that I immediately went down a rabbit hole of like, okay, can I make this? And the answer is yes, but I can't get anything hot enough to ignite it.
You can. Oh, I'm not going to tell you what to use. Doggone.
Oh,
I shouldn't be telling you these things.
Blowtorch.
I mean, blowtorch, yes, but like, I don't have one of those.
Okay, so here's what I'll tell you. All right.
Uh,
So when I do a thermite reaction, okay,
Yeah.
I do it outside, obviously, and
Okay.
I do it in. You need something for the rust in the aluminum. So preferably like a like not even like a plastic cup or a plastic cup or something that you're just like, or a little paper plate or a paper cup or something. And paper cup's better because it's better to burn paper than it is to burn plastic. And just something to keep them together, right? So you mix them up, right? And they don't ignite. And then the thing that I always use to light to get the whole thing started is a sparkler. Okay, like a sparkler from a like fireworks sparkler, like the kids
Yeah.
go around with, one of those. Those things actually get pretty hot. You start that up, and they don't like to not keep sparking, so you stick it in, and it goes. But here's the thing: when you're doing a thermite reaction, you have to be extremely careful. Okay,
Yes.
so wear some goggles and stand upwind of the thing, and then you got to make sure that like the smoke or whatever isn't going to get on anybody nearby, right? And you got to do it in a little sandbox. Okay, so you put your little cup inside of a sandbox. So can you do the thing? Yes. Should you be extraordinarily careful about it? Yes. Like preferably you would do the thing like in some open space, somewhere where you wouldn't be able to catch anything on fire, right? So like I'm always really careful. So the place near our school that seems safest to me would be like Fault Line Park. So I wouldn't worry about doing a thermite reaction in the middle of Fault Line Park as long as some people weren't really walking around, right? Like right there on the grass isn't going to catch on fire. It's in between all the buildings or whatever. There's plenty of wind blowing through. It's going to dissipate whatever fumes are evolved. I could have everybody stand upwind. Like I wouldn't worry about it, right? So that's where I would do a thermite reaction. That's a safe spot. So you want to pick some place that's similarly safe for that kind of chemistry if you want to do that kind of chemistry. And you also want to start really small. So start with, just like a golf ball sized amount of initial reactant before you start working your way up to anything bigger, because you don't want to do anything dangerous. Okay.
Right.
Yeah.
So
that's
anyway,
how to actually do a thermite reaction.
Yeah, I just fell down the rabbit hole. I'm reading through the Wikipedia article now. This is going to get me in trouble at some point, but it's not going to be now. But anyway, that's
You
cool.
don't have to get yourself in trouble with the thermite reaction. It's just, it's the thermite reaction is a pretty safe reaction in all fairness, because even though it burns super hot, it's a it's just a hazardous reaction. It's not a dangerous reaction. There's nothing unpredictable about it, right? Like, it just does what it does. So if you set it up as I've described, like, you're not going to run into any issues or whatever. Like, you'll be
Right.
totally fine. It's not going to, this is not an explosive reaction. There's no reason it should be an explosive reaction. Okay. You're not like playing around with trinitrotoluene or toluene or like some
Mhm.
hypoxides or whatnot. Okay. You're fine. Okay. So, all right. So particulate models of the evaporation of liquid water, blah, blah, blah. Okay. So guys, on the count of 3, the answer, 1, 2, 3,
C.
C.
C. Okay. Answer is C, right? And that's what this is showing, right? These arrows are roughly the same going up as these arrows going down, and there are 7 going up and 7 going down. And yeah, that's true. Okay. So like if you go from like, let's just use water, right? H2O liquid goes to H2O gas, right? Like delta H equals X, right? Whatever that is, or delta G equals X. It's gonna be the same going both ways in terms of magnitude. So delta H for the reverse reaction just equals negative X, okay? And so does delta G. Delta G equals negative whatever the forward delta G is. All right. So any questions about this, scholars? Okay. All right. But yeah. Okay. That's it. Oh yeah. So yeah. All right. Yeah. So additional advice regarding the thermite reaction. Okay, if you really like can't help yourself but to do a thermite reaction, then you take a fire extinguisher and a bucket of water with you just in case.
Yes.
And definitely some goggles, okay, for you and anybody else who's watching, and make sure that nobody else is around, okay? And
Yeah.
you might want to get it cleared with the fire department, just depending on where you are. Like, I wouldn't, as a chemistry teacher, I wouldn't worry about doing a small thermite reaction in the park, because the cops wouldn't be giving me grief. Nor would the fire department, and it's a perfectly safe thing to do. Like, I've done this before at other schools, like, it's fine. But you're not a trained chemist yet, so
Yeah.
you be careful.
I've played around enough with molten metal to have a healthy respect for
Yeah, you told
Yeah.
me about that. You guys made a forge. That's still
We-
crazy.
we-
I want to see the video again. Okay,
Yeah.
we should move on. All right, so question 11. Oh, nice. Okay, so you've got H2S and H2O, and you've got delta H of vaporization is 20 versus 40. Okay, so, all right, how many moles of H2S must be condensed to release as much heat as would be condensed when 1 mole of H2O is condensed? Oh, this is great. Okay, so so the table above provides the values for some physical properties of H2O and H2S. Approximately how many moles of H2S must be condensed? So I'll write this on the board. Moles of H2S to provide as much energy as heat as would be released when 1 mole of H2O is condensed. Okay, so this is fun. All right, give this 90 seconds, okay? It's pretty straightforward. Hey Siri, set timer for 90 seconds.
Okay. Your timer is set for 1 minute and 30 seconds.
Yeah, so when we have the time, I've got a brief thing for show and tell of one of what happened when our crucible melted down.
Kate, honest to goodness, if you want to do a thermite reaction with me
Yeah.
while we're, no, Italy, it's the other way around. If you want to do a thermite reaction or whatever and get it on video and we can show everybody, that's fine. Like, I'll go with you. That way you'll have proper oversight.
Honestly, that sounds like a great project for summer break. It's just
No, because they're not equal, Italy.
Yeah.
So it's
Hey,
the same
Dr. J.
ratio but flipped as your initial answer.
Dr. J.
There you go, Italy. That's correct. Yeah, Antonio, what's up?
You done an amalgamation?
I did a thermite reaction. Does thermite create an amalgam?
What's the definition of an amalgam? Because it creates.
Yeah, I don't know. Is it just a type of alloy? Like that's a good question. I don't.
Oh no, it.
I don't know, but I think it's with mercury combines with another metal and it forms an amalgam.
Okay, it's got to have.
As far as I know.
Mercury and gold, I think, make an amalgam. That's why gold mining was so toxic.
Looks pretty cool.
Yeah, I don't know. I don't know what amalgam means exactly. I mean, I remember I had amalgam fillings, and yeah, they had mercury. Amalgam. A mixture or blend. No, it just means mixture or blend. But in chemistry, it says an alloy of mercury with another metal, especially one used for dental fillings. Yeah, that's how they made your old dental fillings back in the day. So like now they're like some kind of composite. I don't know what they are.
Yeah.
But back in the day, they were made with mercury, and they would actually put that into the amalgam. They'd put it into your mouth. I had these old metal fillings when I was a kid. Okay. So the table above provides blah, blah, blah. Okay. Okay. So guys, what do we get for the answer for this one? On the count of 3, 1, 2, 3.
C.
B.
Some of us got B. Okay. So look, the delta H for vaporization of this one is 20. The delta H is this, right? So you got to condense it. Okay, condense. So it's releasing energy, right? So you got to have 2 moles of this to equal what the energy released by 1 mole of water, because this is kilojoules per mole, right? So the answer is C. Okay, who has a question? Yeah, who has a question? No question? A bunch of us got this wrong. We should be asking questions. Symphony, what did you get? Symphony?
I got C. for
You
that
got
one.
C. Okay, good. All right. Ethalie, you got C, didn't you?
Yeah, I got C.
Okay. Any questions, guys? All right. So, okay. Let's move on. So we're going to go to number 12. Okay. Okay. So the heating curve for 1 mole of, looks like N2, initially at 25 degrees Celsius, shown on the left. Which of the following best explains the, what is that, N2? What? Sodium, Na. Na, that's Na, sodium. Okay, that's not N2. Okay, at 25 degrees C on the left. Which of the following best explains the change in heat when 0.5 moles of sodium undergoes a transition shown in the diagram above to the right? Okay. Oh, yeah, this is fun. Okay, the change in heat, right? So, okay. So try to figure this one out, okay? This is one of those phase diagram problems that we went over. So we went over it really briefly, though. So we could have spent more time on this. I just didn't know how heavily it would be tested, but it looks like it's going to be tested reasonably heavily. So, okay, give this guy 90 seconds and we'll start talking. Hey, Siri, set timer for 90 seconds.
Your timer is set for 1 minute and 30 seconds.
Okay. What happened, guys? Did something happen with my screen share? Can you guys hear me? Hello? What? Can you get what? Okay, looks like the screen share got goofed up. There we go. Can you guys see this, the share now? Hello? Is everybody here? Can anybody hear me? What happened?
Okay. But is this one of those?
There's two of you.
All right. So can you guys hear me now and see me?
Yes.
Okay. I just don't know where this thing is happening. I'm going to stop this recording.